of inertia, which we symbolize with a big I and has units of kilograms meters squared, this is the rotational mass, or the rotational inertia, basically the resistance to any change in an object's rotation, how quickly it's spinning around. In the same way that mass is the thing that resists any change in the object's translation, how it's moving from place to place. So if it's speeding up or slowing down, the mass is the thing that's mediating that acceleration in Newton's second law, F equals ma. So the moment of inertia is, like I said, kind of the rotational mass. That's how we can think about it. And the equation that we use to find it, the moment of inertia, is the integral of dm, which is an infinitesimally small bit of mass, times r squared. So let's just define these. dm is an infinitesimal bit of mass, a very tiny on the calculus scale bit of mass, and r is a distance, and it is the distance from the axis of rotation. Which is the line that this object that has a moment of inertia, it's the line that the object's sort of rotating around. So we'll talk a little bit more about that later. And just as a little bit of background, why the name is the moment of inertia, which is kind of a strange name. Well, in physics, moment is some property, some physical property, in this case the mass or the inertia, times a distance. And then you can number them according to what power the distance is to. So formally, this would be the second moment of inertia. Second because it's r squared, moment because it's the distance r, and of inertia because it's of the mass. The physical property that we're multiplying by the distance squared is the mass or the inertia. So that is the formal definition of inertia. If we're lucky enough to have mass in tiny little locations where you can say all the mass is at the same place, which in that case, if we have point masses, so all mass at one location, then we don't have to do an integral. Then we can do this guy. We can just do a sum of each mass multiplied by the square of its distance from the axis of rotation. And we'll do that from the first mass to the nth mass, however many masses we've got in our system. So for example, say we've got a little dumbbell. So I don't really have a little dumbbell, but I made one with some gummy candies. So if we take, in our example, a little dumbbell, and we rotate it about the center here. So that would be a rotation like this. Maybe if we do it from, let's say, a top view, it would be a rotation like this. So we've got our little masses here, got the length of the rod here, like that, and then we're rotating it like this, around this middle line. So trying to do this rotation here. In that case, this guy would be our axis of rotation, which from now on I'm going to do AOR to symbolize that. And let's just say that this length is L, half the little rod, and we'll do a massless rod, by which we just mean that these dumbbell weights on the end have a lot more mass than the rod, so we really don't have to consider the rod. So in that case, what is the axis of rotation here? And we'll call this configuration A. Well, it is going to be the sum of the masses and their distance. And so we'll do this first mass. Its mass is just m. Its distance from the axis of rotation is L. So we'll put an L squared for R. And we've taken care of mass 1, and then we have this second mass over here. And it also has mass m, and it is also a distance L away from the axis of rotation. So here, the moment of inertia is 2m L squared. What if instead we rotate it about one of the end weights? So the exact same object with the rod length 2L, but now the axis of rotation is here. So this is a bit more like we're holding this and then swinging it around like that, swinging around the end weight. Okay, so then for this new configuration, we'd add up the first mass, its distance, plus the second mass, and its distance, and the first mass, still m, but the distance, well, it's on the axis of rotation. And if we're assuming it's a point mass, that is all the masses at one location, well then its distance from the axis of rotation is 0. And then the second mass still has mass m, but now its distance from the axis of rotation is 2L, like that. So this part, 0 squared is 0, and 0 times anything is 0. So that whole first term is 0. And the second part, if we square the 2L, we get 4L. So 4mL squared. So you can see that mass matters, but distance matters more because it's squared. So having two masses a length L away will get you a smaller rotational inertia than having one mass a distance 2L away. And just to emphasize that point, we could do a third configuration. So here's our little dumbbell again. And the length here of the rod is still 2L, but what if we rotate it like this? Now that's our axis of rotation. So that would be like we have the little dumbbell like this, and we're rotating it around like that. Well, if we're assuming that, again, these are point masses, all of the masses at the same location, then the moment of inertia here, our first mass and its distance from the axis of rotation squared, plus our second mass times its distance from the axis of location, well, both of these guys are on the axis of rotation, so their distance is 0. So here, the moment of inertia is 0. If these guys are really point masses, then there is no rotational inertia. There's no resistance to any change in the rotation here. So you can see how distance really matters and how you have to pay attention to where the axis of rotation is, even for the same object, because you can get very different moments of inertia. All right, now of course, dumbbells are not actually little point masses. Instead, they're like spheres, and they're pretty uniform, so the density is pretty uniform. The mass is spread out equally throughout the spheres, but it really isn't quite right to say that all the mass is at one location. So let's look how we could actually figure that out then. Okay, here we're going to use something called the parallel axis theorem. So you read about that in the textbook. And hopefully saw or remember that the equation to find it is if you're finding the moment of inertia of an axis which is parallel to an axis of rotation which goes through the center of mass. So just to remember, that's the center of mass. It's going to be that moment of inertia plus the total mass of the object, and then the separation between the two axes. So between the parallel axis of rotation and the center of mass axis of rotation. So for the dumbbell, let's see how this goes. So a little more realistically speaking, we'd have a solid sphere and then another solid sphere. And we're still going to assume that the mass is, or the rod is massless. So let's do this configuration where we're spinning it about the center axis of rotation. And we still got our length L here, and just so we can have some numbers, we'll say this is about 1/2 meter. That seems kind of reasonable for, you know, a big old stage dumbbell. And the mass might be 10 kilograms, and then the radius, sort of from here to here, maybe that's about 0.2 meters or 20 centimeters. Okay, so if we go look in figure, what is it, 1020 in your textbook, if you have a uniform solid sphere, they tell you that the moment of inertia is 2/5 the mass of the sphere times the radius of the sphere squared. And it makes sense that it's 2/5. It's less than the mass times r squared, because if you've got a solid sphere, a lot of the mass is closer in than just the full radius. And this is if we rotate through a diameter. So for this moment of inertia here, we'll do it in blue. It's as if we're rotating through that diameter. So this here is the center of mass. So if the sphere's uniform, that diameter is going to go through the center of mass. So this is our center of mass moment of inertia. And then here, this is the axis of rotation we're actually interested in, the parallel one. So this here is that distance d, the distance between the two axes. So in here, that's equal to L, the length of half of our rod. So if we want to find the moment of inertia of the whole system, we're going to need to find the moment of inertia of this mass. So we'll call that the mass on the left. And then we're also going to need to find the moment of inertia of this mass. We'll call that the mass on the right. So let's do the mass on the left first. All right, so according to the parallel axis theorem, we'll need the center of mass moment of inertia, which is this guy, the line going through the center, the middle of the sphere. So that is 2/5 the mass of the sphere times the radius of the sphere. And then we need to add it to the total mass of this left sphere, so that's m, times the distance between the two axes of rotation. So in that case, this is just L, this length L here. So L squared. All right, so we've done the left one, now we need to do the right one, and we can see that, oh, it's exactly the same situation, just over on the other side. But since all the distances are squared, it doesn't matter which direction it is. So the right dumbbell weight is going to have the same moment of inertia. That parallel center of mass, the center of mass moment of inertia, plus the total mass times the distance between the two axes. And so our total is going to be this left one, so 2/5 mr squared plus ml. Oops, and those should be the same m's. And then our right one, which again will be 2/5 mr squared plus ml squared. All right, so we got two of these guys, so we'll have 4/5 mr squared, and two of these guys, so 2 ml squared, and then I guess we just plug our numbers in. Well, 4/5, that's going to be 0.8. Mass, that's 10 kilograms. R squared, that's 0.2 meters squared, plus 2 times the mass, 10 kilograms again, times L squared, so 0.5 meters squared. 0.8 times 10 kilograms is 8 kilograms. 0.2 squared is 0.04 meters squared, plus 2 times 10, that's 20 kilograms, times 0.5 squared, that is 0.25 meters squared. 0.32 kilograms meters squared plus, I guess this will be 5 kilograms meters squared, or 5.32 kilograms meters squared will be the moment of inertia for this dumbbell setup, where we don't have point masses, but instead we're paying attention to the masses sort of in this big solid sphere.